So questions on site and then also online. So we have to figure out how to do this. But yeah, on site. Okay, let's start from here and then go back.
Okay. Hi, Konrad. Stefano Panzeri here. And I have a question about your concerns about being impossible to reconstruct causal relations from neural network observing the activity. And I wonder whether your concerns would apply to experiments in which not only you record neurons with individual precision, but also you can manipulate them, switching on or switching them off with two-photon optogenetics. And I was thinking while you explain these limitations, which I agree with, but my impression is that for those experiments, at least you can reconstruct causal relationships and then maybe put them in a model or a language that could give you some idea about the function. Or do you think that even that approach is flawed logically with the same?
No, thanks so much. This is a wonderful question. So indeed, and to make sure that everyone's on the same page, we have these modern techniques, say optogenetics, or older techniques, even electrical stimulation, with which we can specifically perturb the brain in a given way. And this is a perfectly fine technique that establishes that there exists a causal chain from where I stimulate to where I record, where I see an effect. If I do it randomized, it is the equivalent of a randomized control trial. It's a perfectly fine way of reading out causality. Now, let me maybe break down why I don't see this as ultimately a solution to the things that we want to do there. The first thing is it is very low dimensional. Like I will do that to that one neuron, and that's great. And I can see what are the downstream neurons of that one neuron, no problem. That works perfectly fine. It's logically consistent. It's just that if I wanted to do that to all the neurons, then I'd have to do this experiment 10 to the 11 times, and that is going to take a long time. There are no methods of doing it in parallel. Now you could say, well, what if I stimulate at 10 places? What if I stimulate at 1,000 places? As I start stimulating a lot of places, I'm adding noise to that perturbation. So there's a fundamental limit on kind of how much perturbation I can do. The next point is in that domain, power is very difficult. Like if I have one neuron and one output neuron, sure, I can do that for 10 minutes. But if I wanted to do that for, let's say, 10 source neurons, it would be 10 times slower. So ultimately, we run into problems there. So yes, like these techniques are wonderful, and those are the best we have in that area. But it turns out that the way computation actually works is high dimensional. So you can say, well, I can TMS like a brain area. I can take like V1 or something. But V1 sends like all the information, lots of information about the visual environments to lots of different sources and gets inputs from lots of sources. So this one-dimensional hammer that I have, like boom, extra spikes in V1, that doesn't allow me to understand kind of like this how like all the individual neurons have causal effects in all the other areas, and that trivialistic view where it's basically each brain region just sends one-dimensional signals, that is certainly for a lot of the interesting brain regions involved in like perception, action, thinking seems entirely unjustified. But you're absolutely right. Like the way to and arguably, and I want to hold that point, that arguably the only way to learn about which brain regions influence one another, or like which neurons influence one another, is to do perturbations.
It's me, my turn. Okay, hi, Konrad. It's Beate from Philosopher. So thank you for your talk. It was really interesting. I have one quick comment and a question. The quick comment is on how neuroscientists apparently use the term reduction and causation, and somehow that it is always in one sentence, which is interesting because philosophers of neuroscience usually say, no one believes this anymore, that you can study these pieces in isolation and that they are so simple. You need to study these more complex systems, but they still would talk about causation. So they wouldn't talk about this in one breath. But my question is, do you have a definition of what a confounder is? And I was wondering, what do you mean by saying that all the 10 to the 11 neurons are confounders? Do you mean that they're actual confounders or something like potential confounders?
Yes, let me break down all these. Like this is wonderful, because I think this is the discussion that we should be having. So the first thing is there is a disconnect there. You're right that if you probe a neuroscientist about their commitments towards reductionism, towards that naive idea that we have these specialized things and we can understand them by zooming in, they will all say, yeah, we kind of don't really believe it. But then you read their papers, and the entire paper is predicated on that assumption being right. So I think that distinction is very important to me, and I'll be moving towards confounding. 1 second. So let me first put up like a super clean definition of causality that I believe almost all neuroscientists share, despite whatever they tell the philosophers, which is A causes B in the brain or otherwise. If we would have reached in and would have changed A to a different value, then the probability distribution of B would have been different. In other words, if we would have gone in and stimulated that neuron, that other neuron would have done something different, and that's what we call causality. Now, let's talk about what confounding is in this case. If we have two variables, A and B, that we now only record from, under certain circumstances, we can figure out how A influences B based on recordings from A and B. Now, confounding is any variable that affects both A causally and B causally. So now what that means is, my definition of confounding is C is a confounder for the AB relationship if the probability of A changes if I change C, and the probability of B changes if I change C. So there we have a very clean definition of causation. Now, why do I say that all other neurons are confounders? In the brain generally, from every neuron, there exists a path to every other neuron. And in fact, we can do that by putting rabies into one neuron, which will like step by step basically label the bulk of the other neuron, the vast majority of other neurons. So therefore we can directly map out that every neuron confounds every other neuron. And that's why I'm saying that there's 10 to the 11 confounders. Now you could say, Julia-Paul type, we have relationships where we have the vector criterion that we record, but it would still mean that we'd need to record from the right order 10 to the 4 neurons to produce that condition, which again isn't going to be, we will not be powered to even do that for the corrections.
Thank you. We have one question online. Igor, I think, yeah, you can go ahead.
Hi, can you hear me? Okay.
Very well.
First of all, thank you very much for your great talk and for the input you are giving to the field with your papers as well, because I think this has been very important. Second, I'm behavioral scientist, and not as a technique, but as a perspective in approaching the field. And so my view is based on behavior controlling the brain, and not vice versa, though the brain generates behavior. So I'm very much focused on behavior as a critical level of analysis, and behavior is an emergent property. And so my guess would be that the causality at the level of the emergent properties cannot be explained at the level of the components. So could you comment on this? Because I as a behavioral scientist, I see very often causality. I see it by dog. In my dog, I see causality myself and many others. So I think this scale problem is a key issue.
Yes, there are so many levels to the answer that one should give to your question. So I will only be able to do a very small piece. So the first thing is the theory space when it comes to behavior. The field is basically dominated by non-causal theories in a way. Like the theories that dominate behavior today are mostly normative theories, and the logic is very simple, where we basically say there exists a problem that the human needs to solve. Let's assume that brain is good at solving them, including uncertainty and optimal control, and you name it. And ultimately, that normative assumption gives us a theory space with a lot of theories that are really good at predicting what people and animals will do in given situations. So that's one level. So that is kind of, so if you want, the theories that are of the causal within the brain region, within the brain logic aren't effective in behavior. So very few people say the reason why they move this or they do this 2AFC thing is because this is specifically what's going on in the brain. And these theories are usually much worse than the normative theories. But coming back to causality, like there's no doubt that human behavior is characterized by causality, and our experiments are characterized by causality. If I show you a stimulus, and that stimulus is randomly drawn from a set of stimuli, I totally establish that there is a causal influence of the stimulus on your behavior. So there's no problem in that sense. But it's also, if I put you in front of a device, you will assume that within the device, there's a causal chain that you can learn about and do something about. And Alison Gopnik and many others have kind of shown that even starting at the age of kids, we're like building these causal models, and we have, our curiosity is incredibly targeted at figuring out these causal chains in the world around us. So, but that leads to that funny thing, where you have a normative theory wrapped around causal models of the world that we fit to human behavior. So it's like a Russian doll with causality on the inside, but it is not the kind of causality I'm telling this audience to be impossible. So it's a specific property, and this is something that I only realized relatively recently. There's a specific property of the human niche, which is that we build it in such a way that causal relationships in this world are super sparse. Like I'm influencing you right now. There's like a lot of there's like billions of other humans on this planet, but they don't influence you right now because you're listening to me right now. So so basically we designed an environment for us that is causally incredibly sparse, and where causal relationship, where there's a meaningful ontology over causal relationships. And that's why kind of like we can produce these strong causal models in our niche. It just turns out that within the human brain, this assumption about the human niche of sparse causal relationships with like rich ontologies doesn't carry over. Lots of neurons affect millions of other neurons, and it kind of isn't sparse in the sense that a neuron has at a given point of time a causal influence over thousands of other neurons. And therefore, our way of thinking as humans doesn't carry over constructively into neuroscience.
Thank you.
Okay, I'm gonna jump in, and I think the rest of this depends on if Konrad stays for the discussion at the end, because we have 30 minutes buffer there, which we can kind of use it, some of it now for more discussions if you're not staying. Otherwise, we can just pass everything there.
Yeah, I'll have to run, unfortunately. I'm
Okay.
here in a hotel room with my kids.
Yeah. Okay,
They will give me a hard time otherwise.
Okay, so we kind of maybe shift everything for 10 minutes. If there is more questions here, then we can ask. We were going that way. So one on site here. Yeah.
Hello. Thank you for the very interesting talk. I'm actually gonna still ask about the causality. There are recent approaches. Konrad, can you hear me? Because I see someone.
Yeah, I hear you very well.
Thank you. There are recent approaches arguing that entropy could be something that we could focus on to study causality, even without like interfering with the system or changing it ourselves just by pure observation. But if we measure entropy, or specifically, for example, transfer entropy between brain states, we can still infer some causality from that. Like, for example, even resting state fMRI, bold signal, which is, I think by many is thought not to be a good way of studying causality at all. There are recent papers published that say if we, for example, study effective connectivity, not just functional connectivity, which has directionality, and then measure the entropy, when we say from A to B, we know the direction of information flow, we know there is a change in entropy, could we then infer causality? So what are your thoughts on that?
Yeah, so I think that is complete wishful thinking with no meaningful evidence, and I think it's also a trick. So if you talk with the statisticians developing these techniques, they are open about the assumptions they put in, things like unconfoundedness. You tell them that, but the brain is confounded, and here's why, here's how. They're like, okay, yeah, then our methods don't apply. But the customers of those statisticians want to misunderstand what the statisticians say because they want causality. Like, that's the thing. Us neuroscientists, based on how we came here, we so deeply want causality that we are willing to say the darndest things just to avoid having to face that we can't get at causality. Now, let me talk specifically about transfer entropy. Transfer entropy is one specific algorithm. Like, data goes in, the algorithm does stuff with it. There is nothing at all that protects transfer entropy from confusing, confounding for causality. Like, it just shows up as joint information. Like, transfer entropy, it's not this magical thing giving you anything specific. It's just a way of quantifying certain related pieces of information. In other words, it's just souped up correlation. Like it's just souped up correlation put into words that are so complicated that the users of the techniques no longer see that it's just souped up correlation. And so transfer entropy in no way establishes causation in any way that correlations don't. It's the same thing. It's just, so there is this thing where if the statisticians tell the world, no, the techniques tell you absolutely nothing about causality, they will use words that just make it harder for people to see that it tells you absolutely nothing about it. And this language trick is happening everywhere. And I want to, like, don't trust my words. Like, I'm just one of these people. I'm like doing that math that a lot of others do. You shouldn't trust me. That's why I want to give you the chance to figure it out yourself. Go to the NeuroMatch tutorials. Simulate a number of neurons. Make it be 100, make it be 1,000, make it 10,000. No problem. We have modern computers. They can do all that. Now, assume that out of these 10,000 neurons, we only record 1%, which is much more than we do in reality. Then put it into the magical algorithm that your statisticians tell you about. And then figure out how similar it is to ground truth. And what I'm telling you, it's not similar at all. So basically, don't trust me, don't trust them either. Just put it in a simulation that you can believe in, add some nonlinearity, make it a lot of neurons, make it that you only observe a small part of neurons, because this, like, nonlinearity exists and we only record this tiny, unbelievably small piece of the overall thing. They're undeniable experimental facts, and then see if what they say works actually works. I've done a lot of these things and I understand the mathematical details behind it, and I convinced myself it's absolutely impossible, and let them show that it's possible. Like, it's very easy to, like, just download whichever package they use for transfer entropy, ask if the output of transfer entropy is similar to what we use for generating these things, and it won't be.
Thanks. Do we have, one more from Klaus?
Hey, so wonderful and great you're stimulating. If I understood correctly, but I may have not, then you're saying two slightly conflicting things. So the first thing is that causality is hard, if not impossible, to establish because of all the confounders. And the other thing is that causality may actually be quite sparse. So not everything needs to be taken into account. So it may boil down again to what you started with, the problem of decomposing the system to little mechanisms that we can actually understand. Would you agree on that? And would you have hope for us by saying that after all, we may discover some ways of decomposing the system in such a way that we can isolate causal mechanisms?
No, I think there's a misunderstanding. I say in the outside world, causality is wonderful and sparse. When I talk with you, or when I learn something from Kaysen about like estimating influences, that kind of interaction, the world in which we humans live, the niche that we built for ourselves is of the nature that it's super, super sparse. Oh, and Clara, say hi. There's everyone there. The world around us is super sparse. The niche that we built is super sparse. But in the brain, that's not the case. So I don't believe that we can get that out of the brain. Now, you can say maybe the sparse world in which we are has a reflection in the brain. And if only we understood the sparseness of the causal interaction in the world, we could use that to understand things in the brain. But like, look, I have blue hair. It's perfectly arbitrary. But your brain now uses it. You could recognize me from a large distance using that as one of the many features to do that. So if you want, in the world in which the brain is written, things are not sparse. The sparse thing is in the outside world. And so you can say a normative model of human behavior would be full of sparse things. But the mechanistic model of how the brain does it wouldn't have that property. And that's why I don't think we can do that with the brain.
I might actually slightly disagree. I think the brain is very sparse, at least in terms of its connectivity. So not everything is wired with everything else. It could not be, of course. And so, in fact, the connectivity is 1 in a million. You know, if you take the number of synapses, the number of elements, of course, it's structured, but it may not be structured in such a way that everything propagates to absolutely everything. But anyways, I just try to keep my hope for, you know, delineating some mechanistical systems out of that confounding space of 10 to the power 11 elements.
No, so just like you can with principal component analysis or something, there is no doubt that there exists structure that we can discover. Like, for example, the world above the horizon is different to the world below that. Like, there's an infinite set of like truths about the world whose reflection in the brain we can ultimately discover if we look for that. The question is, if for the things that are interesting, like human intelligence, those are prompts that we can write in a sparse language, and I strongly expect that it's not. But let me just be clear here. Like, of course, the brain is sparse. Not like a neuron has a cortical neuron has order 10,000 inputs. It doesn't have order 10 to the 11 inputs, but the question is there something that is much more sparse hidden within that? And I'm saying there's not, like that you basically have 10 to the 14, 15, maybe more parameters that are all actually tuned to the properties that the world has around us. And then you can say kind of understanding brains boils down to understanding everything about the world in which we are.
Yeah.
Okay, I think time for your next. I'm so sorry about that.
No problem. Thank you. I think we could continue really discussing. Actually, you have a question in the chat that I was thinking maybe you can also answer it in the chat. That might be easier. So we can set up the next speaker and then move on, and maybe later keep this up on Twitter as always, or Mastodon now.
Thank you so much for having me.
Thank you for joining us.